Hello everyone, talking about hydromodification management, and now we want to go over the flow duration performance standards. Learning objectives for today, we want to be able to design a measure such as a detention basin that meets hydromodification management performance standards. And why detention basin? Because as I talked about it in the previous slides and lectures, it's one of the most popular and practical types of structural BMPs that can provide flood control benefits, hydromodification management, and also comes with some capture volume for water quality purposes. So talking about concepts, flow duration performance standard, the stormwater model that we use, EPA SWMM, is able to generate a flow record corresponding to the frequency of rainfall data input as its output. So that's its a strength. That's why we're using it a lot for projects like this. And we do need to process this output so we can basically compare the pre-development and post-development flow rate and duration. So not just the flood control board, where we only talk about peak flow and peak flow attenuation. We're also talking about duration in the area of hydromodification management. That's something very important because we're talking about the ability of the flow to cause erosion over time. So that's why the duration does matter. And here is basically the meat of the hydromodification management in terms of flow duration performance. We're talking about, if I'm going to turn on my highlighter, we're talking about two concepts. Basically, we're talking about a range of flows. One side of the range is a 2-year runoff event, 50% of it. That's why we show it with 0.5 Q2. And the other side of it is the 10-year runoff event, Q10. So this gives us a range. Within this range, we must make sure the project discharge rates and duration do not exceed the pre-development rates and duration by more than 10%. So some new concepts involved here, but as I present this more visually and explain some examples, it is very clear and very easy concept to comply with. But again, as a recap, we're talking about a range of flows, 2-year event and 10-year, why not anything outside of it? Less than 2-year event, if we're talking about an event that happens every couple months, then it's too minor. It can't cause erosion and channel instability and issues that we talked about it before. Larger than 10-year event, like the event happens every 100 year, it's too large, it's catastrophic. It's where the entire city is under the water. So no one can care about erosion and channel issues like that in such an emergency condition. So that's the range that we talk about. And just so you're aware, for the lower side of the range, guidelines sometimes such as 0.5, 0.3, or 0.1 Q2 as typical threshold values, and it depends on your exact application, which is outside of this lecture. But we're picking 0.5 as one of the typical values. So basically means half of Q2. So in a range between half of your Q2 and your Q10, you need to comply with this guideline for flow rates and durations. So how to do it? Make sure you're all aware that we're dealing with continuous data. So for flood control, it's a single design storm, 24 hours. If it's 10-year, 2-year, 100-year, we're talking about just one single event that causes flooding. Here, we're talking about years of data. So we're doing continuous and it needs to be hourly. So hourly data over like last 5-10 years, we're talking about that. And we need to come up with discrete values of flow rate. So when you run your model, your stream model for last 20 years, it gives you just one large time series of flow values. you need to make them individual events. How to do it? You need to know your thresholds. So these are the thresholds typically suggested for hydromod. To make discrete events, if you have back-to-back rainfall events, so we can't consider all of them as one event because there might be a duration, a long duration, let's say 24 or more hours of no flow. So if you have 24 hours or more of no flow, this definitely you're talking about separate events. But another thing for modeling is that no flow is not something easy to happen. Because of the iterations and algorithms in the model, you might have hours and hours of like 0.00001 CFS. That's definitely something that is meaningless in terms of a flow. So that's why you have a CFS type of threshold as well. A 0.002 CFS per acre. So if your area is of course 1,000 acre, then if you're having less than 2 CFS, that means that you can consider that one as 0. So consider as no flow and see if you have 24 hours or more of that situation, then you're talking about separate back-to-back events. That's very important concept for analyzing continuous data. And now that you have it, then I'm sure all of you are aware of this concept in hydrology, that you can use plotting position by ranking the events from largest to lowest, and you show the magnitude on one axis and the probability of exceedance on the other axis. So just a recap very quick, as suggested by Cha and many other textbooks, wave rule is one of the most popular approaches in this area. So very easy concept. If you have 99 separate events, 99 separate CFS values, and each value, you're talking about different events, each of them has its own peak. So you take the peak, it gives you 99 peak values. You sort them from largest to smallest, and n plus 1, number of record plus 1 is 100 in this case. And your very largest value, whatever it is, it's 11,000 CFS. You don't even bring it to the calculation here. Your very largest value is basically the rank of that one. Your largest value has a rank of 1. 1 divided 100, that means 1% probability to have something larger based on this empirical method. And as you go down, if you get to your super low value, which is 0.5 CFS, that's last rank. It's M is 99, so 99 over 100 is 99%. That means that you expect 99% of the time, if it's flowing, it's something like this, small like this. So basically, the key concept of smaller events are more expectable to happen, whereas extreme events are less likely. So just a recap on that, and now we want to go over some examples to make sure we're understanding how it works. So the two threshold lines that I talked about, you have Q10. So we're talking about San Diego River, very large watershed. You expect to have around 1,000 CFS for Q10. Your Q2 might be 900 or something. So half a Q2 is around 450 right here. So we're talking about anything in this range between those two. And we discard basically, if I want to change my highlighter color, so we discard anything happens outside of this range. It's not important in terms of hydromodification management. So basically what I'm showing you here, if I want to change it now to green, you have a current condition and you're increasing the area of land development as you go down. So for the last case, when you have 2,000 acres of land development, basically you can see your curve is shifting towards right. That's bad. That means that an event like 800, if in the current condition had around 0.18 probability of exceedance, now by shifting it to right, now we're talking about something around 0.3 of probability. So now you have this much increase in having an event or larger than this. So these are examples showing how land development can shift your flow duration curve to right. Other examples, now we're talking about San Diego River, another location. It's near Santee this time. Same concept, by 2,000 acre, it makes it shifting to our right. So now we can see how it's working. So this is for the hydromodification part. Now I'm talking about the management part. We want to do hydromod management. The management part is where you try to bring this back. Now, are you supposed to bring this back 100% or you have some legroom? As I presented earlier, if I go back to that very first slide, you have 10% legroom. So you must not exceed the pre-development rates by more than 10%. So that means that it's not like the flood control word that you want to exactly match. So if it's your criteria, you can be still 8%, 9% above it. So that's something that gives you that legroom. So now I want to talk about all these in our SWMM modeling practice area that I have. In that case, I had a 2-year event of 4.14 CFS. Half of it is just 2.50 CFS. That's the lower side of the range. The upper side of the range, it's Q10. It's 7.34 CFS for the urban watershed that I showed you in previous videos, how you can do the SWMM modeling, how you can add a detention basin. Now we want to make sure if our detention basin can do hydromodification management for us, and if not, then what should we do? So within this range that I'm showing, you need to make sure that your post-project discharge rates and duration must not exceed the pre-development rates and duration by more than 10%. That's the meat of the hydromodification management. And I talked about how to do flow separation if you have back-to-back events. If you do not have anything for 24 hours or more, you're talking about separate events, and you might have very, very small values. But in this example, because it was just a 29 acre, which is a very small case for a hydromodification management planning, but just to show it to you how it's worked, 29 acres multiplied by the threshold I showed you earlier, then that means that you can set this as your basically limit. If numbers are smaller than this, these are just internal errors of the algorithms and they can be ignored. So let's get this done. Let's go to SWMM and see how we can work with this and how we can create a plot like the one I showed you, so we can do hydromodification management, the exciting part. So of course you want to have your pre-development curve. This is my pre-development, nothing is built in it, just a watershed and an outfall. So I just run, but the key difference compared to previous videos is that now I'm talking about basically not only the 2-year, 10-year, 100-year events, but we're talking about basically a rain gauge. And this rain gauge has a basically, if I come to this rain gauge, compared to single event, it's now a series of like some years, like 5 years in this example. I have 5 years of continuous data. So I run it and I can show you what I mean by having a series of rainfall events. So this button allows me to plot things. I want to plot precipitation, and I want to just show it with the exact time. So I'm running from 2003 to 2008, 5 years. You need to have at least a year per standards. The more the better, like 10 years or more than that is good. And if, as long as you have data, if you have 40 years, which is the case for many areas in Southern California, then you should do that. So that's what I mean. So precipitation from 2003 to 2008, I have several events like this. And now I want to see how many discrete flow events I have, the concept that I talked about. So for that, just go to the outfall Now you want to use this button here, statistics. Yeah, so now we can show all those things. What is the parameter that what is the variable that I'm analyzing? Of course, it's the inflow. So it's the inflow. CFS is the unit that is created in this watershed and being drained to this point. So our events are event dependent. We're talking about maybe one event is 2 hours long, the other event is 68 hours long. So the other options, daily, monthly, annual, we're not talking about that. And if you have an event like a rainfall runoff, so are you talking about the mean value or you're mostly concerned about the peak value? That's the right choice. So we're only talking about these peak values during each event. That's the one that means most for water resources management. So these are the setup and now the threshold that I talked to you. So the one that I showed you that you can discard if you have anything less than that, it's 0.002 times the area. In this case, it becomes 0.06 CFS. And separation time, 24 hours is what they suggested in the guidelines. So now you have it, you can run this. It gives you a summary, how many events you have. It gives you 113 events, mean value, maximum, and everything that you need. Period of the record. So these are just something good that you keep note, but we're yet to see the most interesting parts. So this is the super helpful part that can give you the data that you need for hydromodification management. And I talk about it later. Just quickly show you histogram, how many events you have for each CFS range, and also the frequency plot like the one, but we're basically taking the data on this event tab by edit, select all, edit, copy to clipboard, and then paste in Excel. So yes, so I have it already pasted here. So I'm actually putting it here. You see how it happens, basically paste it here, and everything appears in the right place. This is what we need to comply, but not 100%. So you can have 10% exceedance compared to this. So if your 9.3 CFS value has a exceedance probability of 0.88, then you can work with basically 1.1 times that value. So that's how I'm creating this column. So it gives me the extra room that I actually can use. So this is for the part, we're only talking about the pre-development condition. And now, of course, I have a model, so I can save the result of this one. Then, of course, I have a model that basically a post-development, but there is no hydromodification management. I just using this to see how bad is the situation if I don't do any detention basin or anything. So you run this, and then after that, you always pick the point most downstream of the watershed, but this is where they're later going to add a detention basin. So that's the point of comparison for me. And same details for this window. I need to select an object. I thought I did, but yeah, let me do it again. Okay, this is selected, J out, and sigma sign. Okay. I'm getting this. Yes, so I needed to add that. So now, okay, it, then I maximize it so I see it better. Again, under events, edit, select all, copy to clipboard. Now I'm pasting it here in a situation that I have basically, yeah, so this is how I'm copy pasting. You can select different parts. So I'm pasting it here. So this is another condition. And after that, I have another model, the one that comes with the detention basin. So the detention basin that I designed for flood control, it might come with hydromodification management abilities the way I need it. So I might not need any modifications to that. I can use it as is, or I might need to make some orifices smaller or do some changes like that. So I comply with hydromodification. So this is the one with hydromod. I open it, and in this one, you can see the detention basin. Of course, you want to run it. After you run it, then you pick the same point of comparison and you do the sigma part. Okay, events, you select all, you basically select all, copy to clipboard, and now paste it in another area of Excel. I already done that, so I'm just paste on top of it, so nothing would change. Now that you have this, you need to create this figure. So I'm going to zoom in a little bit on this figure to see what's going on. So the two lines for threshold, so Q2, that's basically actually 0.5 Q2 I'm doing in this example. That's the value I have, 2.05. So that's this line. If you want to make it red so you see it better, that's your boundary line. The other one is Q10 in that watershed that I showed in previous slides and I explained is 7.34. So these are the two lines that you need to comply. And let's start one by one. So this is the one that I have. Hydromodification doesn't exist in this one. It's just post-developed. So I can add data labels. So basically, if I want to do that, select data. So this is the one that has with hydromod or with basin. So this is post developed with basin. And I also want to make sure I'm showing the labels. Legend. So that's post developed with basin, blue line. And I want to label other one so you can see what's going on. So yes, number 4. Number 4 is what I defined for post-develop. Post-dev, no basin. That's the gray line. That's the worst one. And this is pre-dev. So you can see what's happening, and basically how we're plotting this. If I want to show you an example like this one, the worst one. So my x-axis is the event. Basically the exceedance frequency. This is the one that comes with SWM. SWM already does that for you. So yes, you want to pick y-axis as CFS and exceedance frequency as the x-axis. Okay, let's see what we have so far. We have our blue line, post-development with retention basin. It's still above the green line. The green line is pre-development, but for pre-development, we know that we can multiply by 10%. So that's why I have the peak values here, 9.3. I have multiplied it by 1.1. So to adjust the name, it's 1.1 times pre-dev for this green line. So that's our line that we need to comply, but we're still above it. And then that means we need to do some modifications to our detention basin. So going back to our stream model, let's see how we can release the flows slower so we get to a flow duration curve around this green line. Going back to stream one more time. And here is the set of our orifices, and here this is our lowest orifice for water quality for 2 year and above. This is for 10 year and above, and this is our weir. So of course we're not in the area for super small flows. We're around 2 year and above. So this is the one that needs some modification. So I edited here. What I have so far is 0.5 for the height and 2 feet for the width. So let's see if we make it smaller, make it 1 foot, what happens. And just keep in mind, this entire process is iterative. So you need to do changes iteratively and see what happens to your results. So I run the simulation. It's gonna take some time for 5 years of data that I have. So we're about 1 or 2 years in now, right now. Around 50% progress. %75%. Okay, and we are now done. So now we have this. Going back and select the outfall line for the basin, get the statistics that we want, make sure thresholds are set correctly, okay it, and number of events, everything, edit, select all, edit, copy to clipboard, go back to Excel. Now you can basically paste on top of it. So let's keep an eye. Our goal is that we shift the blue line down closer to green line. So let's paste on top of what we had. And you can see now we're done. We are below the limit. So we made it, we made some adjustment to the width of the orifice for 2 year and above, and now we're good. So you can play around. If you want to make exactly match, you can now change maybe a slightly bigger sizes like 1.5 or stuff like that. But this is the whole process of hydromodification management with the detention basin. And I hope you enjoyed this video.